Hello, and welcome to this presentation on number systems. This presentation is broken down into two parts. In this part, we're going to look at conversions from the denary system to the binary system and from the binary system to the denary system. Presentation overview. This is part one of the presentation on number systems, and in this presentation we'll look at the conversion between the binary and the denary systems, and also from the denary to the binary system. A separate video covers part 2 of the number systems presentation. Here are some definitions that we'll be referring to within the presentation. The denary system. The denary system, or the decimal system, is a number system based on the digits 0 through to 9, and it's a conventional system we use in everyday usage. We refer to integers. Integers are whole numbers such as positive 5, positive 12, positive 56, positive 4096. They're all termed positive integers. Negative 9, negative 15, negative 192 are termed negative integers. Between the positive and negative integers, we have the number 0, which is neither positive nor negative. We'll also use the term decimal fractions. A number such as 263.29 is termed a decimal fraction. A decimal point separates the integer part, which in this particular case is 263, from the fractional part, which again in this case is 0.29. We're also going to use the process of long division within the presentation. Long division is essentially a step-by-step method for dividing one multi-digit number into another multi-digit number. So if you're familiar with that process, that's useful. Computer numbering systems. The system of numbers in general use is termed a denary or decimal numbering system, where the digits of 0 to 9 are used. This system has 10 different digits from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and is termed to have a radix or a base of 10. The denary number, 521.6, can be written in what's called a column heading format as shown below. We have 10 to the power 0, don't forget anything to the power 0 is 1, 10 to the power 1, 10 to the power 2, 10 to the power 3 to the left of the decimal point, and to the right of the decimal point we have 10 to the power minus 1, 10 to the power minus 2. This is called column heading format. So the number 521.6 can be written as 5 hundreds, that's 10 squares, 2 tens, that's a 10 to the power 1, and 1 unit, that's a 10 to the power 0. We've got 6 tenths, that's 10 to the power minus 1. So from the column heading format we can write this as 5 times 10 squared plus 2 times 10 to the 1 plus 1 times 10 to the 0 plus 6 times 10 to the minus 1. So the sum of the terms comprising a digit multiplied by the base raised to a power provides a number. This is a basic method we'll be using to convert any number into the denary system. Conversion of binary to denary. To change numbers to the base of 10 from any other base, we use the column method. So convert from the binary system to the denary system. We note that the binary system has a base of 2. So given the number 1011.1, that's equivalent to, in column heading format, of the following. To the left of the decimal point we've got 2 to the 0, which of course is 1, and this into the power 0 is 0. We've got 2 to the 1, which is 2. We've got 2 to the 2, which is 4, and 2 to the 3, which is 8. To the right of the decimal point we've got 2 to the minus 1, which is a half from your negative indices. 2 to the minus 1 is 1 upon 2, so it's a half. And we've got 2 to the minus 2, so that's 1 upon 2 to the 2, or 1 upon 4, a quarter. So given a number 1011.1 in binary, we can evaluate that as 1 times 2 to the 3 plus 0 times 2 to the 2 plus 1 times 2 to the 1 plus 1 times 2 to the 0 to the left of the decimal point. To the right of the decimal point, we've got 1 times 2 to the minus 1. So evaluating that, 1 times 2 to the 3, that's 8, plus the 0 times 2 to the 2 is 0, plus 1 times 2 to the 1 is 2, plus 1 times 2 to the 0 is 1. So to the left of the decimal point, we get 11. To the right of the decimal point, we get 0.5. So in other words, the binary number of 1011.1 can be written as 11.5 in denary. Conversion of binary to denary continued. Here's example 1a. I'm going to use the column method to convert 11110 in base 2 to a decimal number to the denary system. Again, using the column heading format, to the left of the decimal point we will have 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5. Don't forget 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16, and 2 to the 5 is 32. To the right of the decimal point in the binary system we would have column headers of 2 to the minus 1, which is 0.5, 2 to the minus 2, which is 0.25, 2 to the minus 3, 0.125, 2 to the minus 4, 0.0625, 2 to the minus 5, 0.03125. So from the question we read the binary number of 11110.0. So looking at the column headings, that means we've got 1 times 2 to the 4, which is 16, plus 1 times 2 to the 3, which is the 8, plus 1 times 2 to the 2, which is 4, plus 1 times 2 to the 1, which is 2, plus the 0 in this case. Adding the numbers, we get 30. So in other words, the binary number 11110 base 2 is equal to 30 in base 10. Again, I've written it here with the binary number suffix 2, and I've written it with the denary number suffix 10, but the suffix 10 is optional. Conversion of binary to denary continued. Example 2a. We're asked to convert the number 0.1101 base 2 into a denary number, and again using the column method. So in the binary system we would have column headings to the left of the decimal point of 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, and on the right hand side we'd have 2 to the minus 1, 2 to the minus 2, 2 to the minus 3, 2 to the minus 4. In this particular case we're just looking at a fractional part of the number, and we're given a number of 0.1101 in binary in the question. So using the column heading method to work out this in denary, we simply multiply the digits by the column headings. So we get 0.1 times by 2 to the minus 1, which is 1 times 0.5. We get plus 1 times 2 to the minus 2, which is 1 times 0.25. Then we get plus 0 times 2 to the minus 3, which is basically 0 in this case, plus 1 times 2 to the minus 4, which is plus 1 times 0.0625. If we do the arithmetic on that, we find we get 0.8125. So in other words, the fractional number 0.1101 in base 2 can be written as 0.8125 in base 10. Binary to denary conversions continued. This is example 3a here. We're asked to convert 111.0011 base 2 to a denary number. So my column heading formats to the left of the decimal point will be 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, and to the right of the decimal point 2 to the minus 1, 2 to the minus 2, 2 to the minus 3, 2 to the minus 4. And from the question, our binary number is given as 111.0011. Now using the column heading formats and multiplying by the digits, we will get 1 times 2 to the 2 plus 1 times 2 to the 1 plus 1 times 2 to the 0 to the left of the decimal point, and to the right of the decimal point we've got 0 times 2 to the minus 1 plus 0 times 2 to the minus 2 plus 1 times 2 to the minus 3 plus 1 times 2 to the minus 4. Doing the arithmetic on that, to the left of the decimal point we've got 1 times 2 to the 2 is 4, 1 times 2 to the 1 is 2, and 1 times 2 to the 0 is 1, so we get 7 to the left of the decimal point, and to the right of the decimal point we've got 1 times 0.125 plus 1 times 0.00625. That gives us 0.1875. Hence, the binary number of 111.0011 can be written in decimal form as 7.1875. Here are some tutorial questions for binary to denary conversions, which I would encourage you to attempt. Questions 1 through to 5, the answer given in square brackets on the right hand side, and the solutions are on the following slides. But I would encourage you to stop the presentation and attempt these questions now before reviewing the solutions. Tutorial questions, the solutions here for the binary to denary conversions. This is question 1. For part A, we were given a binary number of 110. So to the left of the decimal point, that will be 1, 1 and 0. So in other words, we get 1 times 4 plus 1 times 2, which gives us a value of 6 in decimal. I'll let you look at parts B, C and D in a very similar way. Tutorial questions, binary to denary conversions continued, is question 2. Part A, we're given the binary number of 10101. So from a column heading formats, that will be 10101. So looking at the numbers there, the digits times the column headings, we will get 16 plus 0 plus 4 plus 0 plus 1. So that's 21 in base 10. Again, I'll let you look at parts B, C and D in a similar way. Tutorial questions, binary to denary conversions continue. Question 3, we're given the binary number in part A of 0.1101. So from the column heading formats, we will get to the right of the decimal point 1101. So we'll add up 0.5 plus 0.25 plus 0.0625 to give us 0.8125 in base 10. Again, I'll let you look at parts B, C and D in a similar way. Question 4. We're asked to summate the following 4 binary numbers and expressing the answer in base 10. So from the question, the first number given, labelled A, is 11010.11, and the second number labelled B is 10111.011. I'll let you look at numbers C and D in the column heading format. We're basically then going to add up the totals in each of the column and multiply by the column heading. So in this case we've got 1 2 to the power 7 plus 1 2 to the power 6 plus 1 2 to the power 5. And looking at 2 to the power 4s, there are 4 numbers in the column, so that's 4 times 2 to the power 4. Looking at 2 to the power 3, there is 1 number in the column, so that's 2 to the power 3. 2 to the power 2, so we've got 3 numbers in the column, so that's 3 times 2 to the power 2. The column of 2 to the power 1, we get 2 numbers, so that's 2 times 2 to the power 1, and we get plus 3 times 2 to the power 0 in that column. Looking to the right of the decimal point, we get 2 times 2 to the minus 1 plus 3 times 2 to the minus 2 plus 3 times 2 to the minus 3 plus 2 times 2 to the minus 4 plus 1 times 2 to the minus 5. And doing the arithmetic on that, 2 to the power 7 is 128 plus 2 to the power 6 is 64, 2 to the power 5 is 32, 4 times 2 to the power 4 will be 4 times 16 plus 2 to the power of 8 is 3 plus 3 times 2 to the power 2, so that's 3 times 4, plus 2 times 2 to the power 1, 2 times 2, plus 3 times 2 to the power 0 is 3 times 1. On the right hand side decimal point, we've got 2 times 2 to the power minus 1, so that's 2 times 0.5. We've got 3 times 2 to the power minus 2, so that's 3 times 0.25, plus 3 times 2 to the power minus 3, so that's 3 times 0.125. 2 times 2 to the power minus 4, so that's 2 times 0.0625, plus 2 to the power minus 5 is 0.03125. If you go through the arithmetic process, you'll end up with the solution of adding the four binary numbers together given in the question. We end up with a denary number of 317.28125. Tutorial questions continued, binary to denary conversions. Question 5. We're asked to multiply the following binary numbers together. The numbers are 101100.1 and 10111.011. Got to express the answer in terms of base 10. The hint given in the question is to first convert the numbers into denary and then multiply. I'll let you look at the solutions in your own time, but basically you're going to take the first binary number given and convert it into denary using the column heading format. So you should find that the binary number 101100.1 is 44.5 in the denary system. Question 5 continued, and then convert the second binary number given in the question into the denary number. You should find that the binary number 10111.011 is 23.375 in the denary system. And then we simply multiply the two numbers together to get the final answer. We're going to look at the conversion of denary to binary for integer numbers initially. The simplest method to use is one of successive division. What we're going to do is divide the denary number given repeatedly by 2, the base, until 0 is reached. After each division, we're going to write down the remainder under a column heading, as will be shown below. The required binary number will then be given by all the remainders. This process is shown now in example 1b. So example 1b. We've got to change the integer of 14 in base 10 to the corresponding binary number, that's in base 2. So what we do first of all is take the number 14, the base 10 number, and divide it by 2. So 2 into 14 goes 7 times exactly, so there's no remainder. So 0 remainder in this case. Notice how we write the 0 remainder. We put it under the column heading of 2 to the 0. Then we continue the process. How many times does 2 divide into 7? It goes 3 times completely. 2 times 3 is 6, and the remainder in this case then is 1. We write the 1 under the column heading of 2 to the 1. We continue the process. How many times does 2 divide into 3? It goes once completely with a remainder of 1. We write the 1 under the column heading of 2 to the 2. Continue the process of division. 2 divides into 1, it doesn't go, so we get a remainder in this case of 1, and we write that 1 under the column heading of 2 to the 3. So our binary number now is given as 1, 1, 1, 0. That's the binary number of 14 in base 10. Note that the last remainder is the left-hand digit of the binary number. The left-hand digit is termed the most significant bit. The right-hand digit is termed the least significant bit, where a bit is defined as a binary digit. So in summing up, 14 in base 10, the integer given, is equal to 1110 in base 2, the binary number. So conversion of denary to binary, we're going to look at the fractional part of the number now. So the fractional part of a denary number can be converted to a binary number by repeatedly multiplying by 2. So don't forget, we're looking at the fractional numbers here. In the fractional numbers we multiply by 2. So for fractions, the most significant bit of the result is the top number obtained from the integer. You'll see this illustrated in example 2b below. Example 2b. We've got to change the denary fractional number of 0.875 into a binary number. So in this process, the fractional part of the number is repeatedly multiplied by 2. So given a number of 0.875, we multiply that by 2, and that gives us 1.75. Now we take the integer part this time, the 1, and we write that under the column heading of 2 to the minus 1. We carry over the 0.75, and now we multiply the 0.75 by 2. That gives us 1.5. The integer part is then written under the column heading of 2 to the minus 2. We carry over the 0.5, and now we multiply the 0.5 by 2. That gives us 1.0. The integer part we then write under the column heading of 2 to the minus 3. So our binary number becomes 0.111. In other words, the denary number of 0.875, so base 10, is equal to the binary number of 0.111. Conversion of denary to binary continued. We're looking at real numbers here. So example 3b, we're asked to change the real number of 27.625 in base 10 into a binary number. So again, we're going to take the integer part first of all and repeatedly divide by 2. So taking the 27, 2 divided into 27 gives us 13 with a remainder of 1. We write the 1 under the column heading of 2 to the 0. Continuing the process, we now divide 2 into 13. That goes completely 6 times with 1 remainder. We write the 1 remainder under the column heading of 2 to the 1. Continue the process. 2 into 6 goes exactly 3 times, so there is 0 remainder, so we write the 0 under the column heading of 2 to the 2. Continue the process. 2 into 3 goes once completely with a remainder of 1, so that gives 1 under the column heading of 2 to the 3. And completing the process, 2 into 1 doesn't go, so that gives a remainder of 1, and we write the 1 under the column heading of 2 to the 4. So the answer reading from left to right is 11011 for the binary number, so we can say that 27 in base 10 equates to 11011 in base 2. That's the integer part dealt with. Conversion of denary to binary continued here, looking at real numbers. Example 3b continued. We're now going to look at the fractional part of the number, and we're going to find that by repeatedly multiplying by 2. So from the previous slide, the fractional part of our number is 0.625. We multiply that by 2, and we get a value of 1.25. The integer part, the 1, is now written under the column heading of 2 to the minus 1. We carry over the 0.25 and we multiply that by 2. That gives us 0.5. We write the 0 under the column heading of 2 to the minus 2, and we carry over the 0.5. We multiply the 0.5 by 2 and we get a value of 1.0. We write the 1 under the column heading of 2 to the minus 3. We now have our binary number of 0.101. That's the binary number. So we can write that 0.625 in base 10 is the same as 0.101 in base 2. Now bringing the results of the previous slide and this slide together, we can write that the number 27.625 in base 10 can be written as 11011.101 in base 2. Here are some tutorial exercises related to denary to binary conversions. Exercise 1b, we're asked to change the denary integer 69 into a binary number. Exercise 2b, we're asked to convert the denary integer of 128 into a binary number. And exercise 3b, we're asked to convert the real number of 102.40625 in base 10 into a binary number. The answers are shown in the square brackets on the right hand side, but I encourage you to stop the presentation here and attempt these exercises. The solutions are shown on the following slides. Conversion of denary to binary continued. Example 1b solution here, you're asked to convert 69 in decimal form into a binary number. I'll let you review the solution. Conversion of denary binary continued. Exercise 2b, you're asked to convert the denary number of 128 into the corresponding binary number. I'll let you look at the solution below in your own time. Conversion of denary to binary continued. Exercise 3b, you're given the real number of 102.40625 in base 10. You're asked to convert that to a binary number. We break the solution into two separate parts. First of all, we convert the integer part into a binary number by successively dividing by 2. So you will find that the integer part of 102 in base 10 becomes 110.0110 in base 2. I'll let you look at the solution. Exercise 3b continued. We've got to convert now the fractional part of the number given in the question into a binary number. So you're going to start with the 0.40625 and continually multiply that by 2, writing the integer parts under the respective column headings as shown in the solution. Ultimately, you should end up with an answer of the 102.40625 denary number is written as 110.011.01101 in base 2. I'll let you look at the solution. Here are some tutorial questions for you to attempt related to denary to binary conversions. 4 questions here, and the answers are given in the square brackets on the right hand side. I'd encourage you to stop the presentation and attempt these questions. Here's the bibliography used to help create this presentation, and again I would encourage you to look at the reference sources. Some are very good here, good background information to the presentation we've outlined here. I hope this presentation has been of help to you, and thank you for viewing.